Hello, everyone. Welcome to the Jones Seminar. Very happy to have my friend and colleague, Luke Zoet, here. Thank you all for coming. Luke's a great scientist, as you will see, doing a lot of very interesting work about subglacial mechanics. He's an experimentalist, does field work, he does numerical modeling, and over a wide variety of topics. We heard about some of his great work on coastal erosion during the lunch today. So today he's going to be talking about experimental insights into glacier slip. He was an undergraduate at Michigan State, our sort of rankings nemesis in the engineering rankings. So, and what did you say? It's like the better version of green and white?
There's a battle for green and white.
Yeah, that's it, yeah. I think Michigan State is winning.
Yeah.
And then was a PhD student at Penn State after that, and then went to Iowa State. So I think now he's at Wisconsin State. I think
right,
that's
yeah.
the follow. Yeah, okay.
Broken the trend.
Yeah. Yeah, he has to go to a school of state in the end of it.
Yeah.
But yeah, he's at the University of Wisconsin-Madison, and has an awesome group and great lab and doing very interesting work. So I won't take any more of your time. Thanks for coming, Luke.
Sure. Well, thanks for having me. It's been great sort of meeting with all the people here over the last couple of days. It's a school that I know a lot of people. I know a lot of the work that's going on here, but it's really hard to get here. And so it's kind of out of the way. And so, this is my first trip up to Hanover. And it's been amazing just sort of see the area, talk to the people. Today I'm going to talk about work we've been doing to try to understand what happens right at where the glacier meets the bed below, the interface. And we've taken a little bit different approach to this than what's typically done in glaciology, in that we've tried to use experimental devices to look at that problem rather than go into the field or use numerical modeling explicitly. And so just to give you sort of an overview, or this picture right here, what you're looking at is a glacier, and this area in front of it is dirt, basically. And this was under the glacier just a few, years before I took this picture. You can see these lines here. These are called flutes. These are sort of areas where the till has been shaped and moved by the glacier over the time and built these structures. But what this sort of is indicative of is, as the glacier is moving over this terrain, it can do a couple things. It can deform that material, it can deform that sediment and move it around. But there's also this sort of complex interaction of right where the glacier sits on the bed, of how it's coupling to that sediment. And what are the mechanics across that interface? And how do they play into how this glacier moves over time in response to the glacier sort of driving, as gravity is driving it downhill? This is a figure that's sort of commonly shown in glaciology talks. It's a surface map of Antarctica, and it's color-coded by how fast the ice is moving at the surface. And what you see is this is a logarithmic scale. Some areas are going relatively slow. Some areas are going really fast, like these areas right here that are in these darker colors. And when you look at that from the surface, what you can see is that it's moving fast, but you don't know what's necessarily giving rise to it moving fast. Is it lots of deformation within the ice itself? Is it things that are happening at the ice-bed interface? If it is things at the ice-bed interface, what's going on there to regulate how fast this is going? Like, why isn't it going 10 times faster than this or 10 times slower? Those are the types of questions that we'd like to be able to address, to be able to make predictions about areas that are moving fast and areas that are moving slow, and why they're moving fast and why they're moving slow. Sort of a classic examination of this problem was in 1952 by a guy named John Nye. And what he did was he sort of broke this down into pretty simple components, right? And so this is looking at the glacier from the side now instead of looking at it from the top. So think of this as basically, this is the surface of the glacier. This is where you would be standing. This is the bed where it meets that substrate that's at the base. If you drilled a borehole from the surface all the way to the bottom and you waited a year and you came back and measured that borehole, it would be bent like this, right? And what Nye figured out was he kind of had some understanding of how the ice would deform. And he went to certain glaciers and he looked at how much they moved at the surface. And he said the amount that they're moving through deformation of the ice, this amount, is not all of the motion. There's something else going on. And that the logical explanation has to be down at the bed, that there's some component of motion from the ice sliding over the bed as it sort of moves down the hill. And in many places, in fast-moving glaciers, It's this bed component, the sliding component, that gives rise to the majority of the motion that you see at the surface, especially in areas where it's moving fast. And so you might have heard of this analogy people use for a glacier. It's like pouring honey on a board and sort of tipping the board and watching the honey move down the board. A better analogy in many ways for how a glacier moves is putting an ice cube on a board and shifting that board. And what happens right where that ice cube sits on the board, that frictional contact at the interface, that's what's going on here. That's what's doing a lot to govern the overall speed of the board, is the friction in that very narrow zone near the bottom of the glacier where all these pieces are interacting. The ice is interacting with the bed and all these other components. Now, the thing that Nye used to understand this problem was that there was a lot of sliding. We call this sliding over the bed right here. But at the time, they had missed this extra component, right? What happens is a lot of the times, glaciers aren't sitting on necessarily hard bedrock, especially those fast-moving glaciers in places like Antarctica or the big lobes that cover the Midwest or places like in Antarctica. They're sitting on sediment. And that sediment can yield, right? It can deform. And so the overall component of motion that you see at the surface is some combination of ice deformation. It's some combination of the ice sliding over the substrate. And if the bed is made up of a deformable material, like sediment, there's some component of deformation of the bed itself. And all three of those things give rise to the overall motion of the glacier. We know that places in Antarctica have beds that are soft. We know it on paleo landscapes because you can just walk around and look at the composition, say this is sediment, here's some hard beds, here's some sediment. In places like Antarctica, you can use active source seismics. So you go to the surface of the glacier, you let off an explosion, the energy goes down, bounces off the bed, which is this, and comes up to the top. And based on how that amplitude of the wave comes back, you can characterize what the bed is made up of. So this is a paper by Atsumoto, and he's showing that for at least parts of Thwaites Glacier, the bed is primarily made up of soft materials. Thwaites Glacier is not all soft materials. Some of it's soft, some of it's hard, which is where the bed is made up of bedrock or unyielding material. But lots of it are soft in general. Now, what we kind of want to be able to understand on sort of a fundamental level is this thing called a slip law, right? What is a slip law? Slip law relates to the driving or shear stress, which are often assumed to be equivalent to each other, to the sliding speed of the glacier. It's the thing that it lets you take the geometry of the glacier and convert it into stresses and then make predictions about how fast the glacier will move. Specifically, how fast it'll move by the ice moving over this granular material at the bed. To understand that, you got to know things about sliding. You got to know things about if the bed will deform. You got to know if it deforms, how readily it deforms, because all those things contribute to the overall motion of the glacier. And all those components of the bed are baked into this slip law. So fundamentally, how fast does the glacier move if we push on it this hard? And how fast does it move if we push on a little bit harder? And building that relationship up. And so there's a couple different ways that this could happen, right? If you're looking at sort of a section near the bed, you could have all of the basal motion coming from the till deforming, right? So that basically the glacier is just moving as fast as the till can deform. And that's what's sort of regulating the strength of the bed material. It's what's regulating how fast it can go. It could be some combination of deformation of the till and sliding over the top of the material. Or in certain instances, the till can behave rigidly. It won't deform at all, and all of the basal sliding is just coming from all the basal motion is just coming from sliding alone, right? These are sort of the full spectrum of what you might expect. Something that's very similar to if the glacier was just moving over bedrock, something where the deformation of the till is making up all of the motion, and this middle scenario, which is a combination of the two things. Now, each one of these has a different sort of mechanical response, has a different sort of sliding response that can occur. So if this is happening, the glacier will behave very differently than if this is happening when you push on it, essentially. Also, we have this complexity that the granular material, the till, I'll just call it till for lack of a better word for now, at the bed of a glacier, isn't uniform in size. It has a wide range of grain size distributions, and you can have big rocks or clasts at the ice bed interface, and those clasts can poke out from the till into the ice above it and affect how the ice is coupling to the bed and how the ice is distributing stress to the underlying bed. And so there's this roughness or this granularity of the till that's particularly important for sort of regulating how these mechanics play into play also. Here's two sort of potential sliding laws. So I'm going to show plots like this throughout the talk, but on the x-axis is sliding speed. So think of this as the glacier going faster and faster and faster. And this is the shear stress. This is basically how much resistance the bed can provide as the glacier or as the ice is slipped faster and faster. In the black line here, this is called a power law or viscous sliding law. It's sort of like what, if you're a glaciologist, sometimes called the Weirtman sliding law. What this says is as the glacier moves faster and faster, the bed pushes back harder and harder and harder. And it can infinitely push back harder to balance out the glacier speeding up. The other side of the coin is this relationship called a Coulomb, where you push on it, nothing happens. You push on a little harder, nothing happens. You push on a little harder, nothing happens. You push on a little harder, and you meet the stress, and then the material starts to deform, but you no longer have a rate dependence. This thing's just a horizontal line. You can't predict which speed you're going to go at depending on how hard you push on it, right? This is very hard in some ways to solve in a numerical model because you lose the rate dependence of the relationship. Now, what you would expect is if the ice was just sliding over a rigid substrate, like a till or a bedrock, you could get a relationship that's like this. But if the material is granular at the bed, like till, and it's actually failing, and all the deformation is occurring through that failure of the till, you'll get a more Coulomb type responses like this. These are sort of two end-member cases that are possible. People have looked at the impact of including these different slip laws in idealized models. This is a paper by Catherine Ritz where she modeled the Amundsen sea embayment. And what she did was she looked at the range of potential sea level rise that you would get from the glaciers in the Amundsen sea embayment by basically changing the different types of slip laws. So Weirtman has this really low sea level rise in her model. Weirtman's a little more, and then plastic is even higher, right? So why this is interesting is you get a 50-fold difference, essentially, in the contributions of sea level rise by changing this relationship, right? So the overall flow speed of the glacier, the overall mechanics of it are very sensitive to what you choose for this boundary parameterization in your ice flow model. So our objective, the overall objective for my talk today, is to try to determine what the slip law is from sort of basic mechanics that should be used to parameterize how ice will move over these deformable types of bed. I'm going to layer in more and more complexity throughout the talk. So how do you do this? It's really hard to do this in the field, right? It's really hard to go into the field and back out a slip law. Basically, you can't isolate the independent and the dependent variables with remote sensing observations. There's too many things. It's combined together. There's longitudinal stresses. There's transverse stresses. Things are changing all the time. And so when you're looking at these in a slip law or in a field situation, or if you drill a borehole through the glacier to the bed, it's really hard to separate all of those different factors and look at just the relationship of how fast the glacier is moving to how much stress the bed is providing, right? To isolate those two things. Drilling to the bed is a good way to try to look at the bed, but by injecting that hole into the base, you've basically changed the subglacial hydrology in a way where it can be hard to differentiate what you're seeing is the result of what's naturally at the base of the glacier, or the fact that you just drilled a hole into it and pumped water in. So you have to separate those two effects. So to address this, what we do is different than what other groups have done. Was we go to the lab to try to figure this problem out. This is the machine that we built at Wisconsin to try to address this. This is the UW-Madison ring shear device. This thing is about 3 meters tall. It sits inside of a giant freezer. This right here, what you're looking at, is a sample chamber. The white part is a load frame. At the top is a transmission that's got a 2 million to 1 gear ratio that drives the whole procedure. The sample chamber is completely transparent, and it sits inside a giant tub of antifreeze. And the antifreeze temperature can be regulated to within 1/100th of a degree. And that allows us to keep the ice at what's called the pressure melting point, which is a really important parameter to meet for understanding these subglacial processes, because it's believed that most fast-moving glaciers have a temperature that's at this pressure melting point. Fundamentally, what it's doing is there's a disk of ice, a ring of ice on the top, and underneath it, we can put anything we want. So we fill it up with sediment, till, from a glacier, and we build this ring of ice on the top. And then we grip the ice on the top, and we spin it at the same rate a glacier spins, and the bottom is held rotationally fixed. And we can measure at different rates at which we spin this thing how much resistance the bed is supplying to inhibiting the thing from moving. The torques are massive, so massive that those giant steel I-beams actually flex in response to it. We drive this thing at the same speed that a glacier goes. It's at the same temperature that a glacier's bed is at. The effective stress are the same effective stresses you see at the bottom of a glacier. So we don't have to scale any of those parameters like you might have to do in like a fault mechanics model. We're actually simulating all of the in-situ conditions in the device during the experiments. This is sort of a schematic of it. So here's the sample chamber. This is what it's blown up. So here, if my arm waving wasn't clear, there's a disk of ice. It's gripped at the top by these teeth. This thing is rotationally spun. In these experiments, there's a till bed in the bottom of it. As this thing moves, we can get deformation in the till if the system allows it. Slip will occur wherever in the system it wants to occur, whatever the weakest link is in the system. Like I was saying, the whole thing sits inside of a glycol bath. And importantly, there's this big ram at the bottom that supplies the stress to simulate the overburden of the glacier, the weight of the glacier, so we can get pressures in this thing that are like at the bottom of the glacier. So the first question we wanted to look at is what happens when you just slide debris-free ice, clean ice, over till like this? Which one of these scenarios do we get? And how does that get complicated when you add roughness or class at the ice bed interface? How does that cause it to deviate from this one where there's primarily small grain sizes in place? What we do, how we build this thing up, is first we in-place a till layer inside of the bed, and we lightly consolidate it to remove consolidation that will happen in the experiment. We then water saturate it. We have previously built the ice ring, and we slap the ice ring on top of the thing inside of this sample chamber. Then we take this whole situation with the ice ring on top of the till, and we push it inside of that load frame. And once it's inside of the load frame, we put a little bit of liquid water on the top, and we freeze this upper platen into it. And so those teeth are frozen right to the top surface of the ice, right? So it's directly coupled to the ice. Then, over the span of several days, we warm it up from -5, where we froze it, to the pressure melting point. And we have tens of thermistors, really high precision thermistors all through the system. We can measure the contraction rate from melting, and so we know when it's at the pressure melting point, and we can start spinning the system. In the experiments where we put class in the bed, we pick these class. This is just an example of one of them, and they're sort of sprinkled around the ice bed interface. So we do one set of experiments with no class, and then we do another set of experiments where the class are present to see how they change this, the ability for the ice to slide over the bed. We can measure all sorts of things. Like I was saying, we can measure the pressure of the ice. This is basically the pressure imposed by the ram. We can measure the water pressure through all sorts of water pressure sensors we have in the till. If we subtract the pressure of the water pressure from the imposed ice pressure, we get what's called the effective stress, this N, which is a particularly important variable when we're trying to understand how these things respond. It's the difference between the two. And we can measure the resultant drag that occurs. And we can do that as we step through ice sliding at different sliding speeds. Here's a time-lapse video of this thing sped up 3,000-fold. So you can see the ice moving from right to left. There's some deformation that's occurring in the till. It's not shearing very deeply. This is just sort of a crappy webcam we have set up, but we also have set up these high-resolution cameras that allow us to track individual grains through the transparent walls and do digital image correlation to figure out how the deformation profile is changing throughout the till as we systematically change the driving speed and the effective stress in the experiment. We also do an old-fashioned method where we just jam beads into the till, and then we spend hours and hours and hours trying to dig them out of the experiment at the end where it's really cold. But this gives us some verification that what we're seeing in the middle of the experiment is reflected on what we're seeing on the walls where the cameras are looking through. And so in this one, what you see is this stack of beads was vertical and it's slightly tilted, and there's a couple missing up here. The reason these are missing is not because there was no beads there, it's because there was so much advection of till out of that zone near the ice bed interface that the beads were carried far away. When we put the class in, if we melt the experiments at the end, we see this kind of interesting feature. So here's the class. The ice was moving this way. The ice was pushing on the backside of the class. It was actually pushing on the class so hard that it was plowing the class through the till. And this little bump you're seeing in the front is a plow structure that glacial geologists see all the time in the field as class get rammed through the till, and they build this little plow, the structure in front of them as they're sort of shoved through the till. What's happening with these plow structures is, imagine this is the ice bed interface. Here's the till below, and this is the ice. As the ice is moving from left to right, the ice is pressing on the upstream side with a viscous flow because the ice behaves viscously. And that stress is being resisted by the till on the downstream side. And the till, because it's a cooling material, has a finite strength with which it can withstand the stress being applied by the ice. And at some point, the till yields and the particle moves through the underlying sediment. And so, to go back in some ways to the main point of this, these are these two hypothesized types of sliding, right? You have this rate strengthening, you have a Coulomb relationship. This is how the till would behave. This is how ice would be sliding over a rigid bed in some simplified ways. And what we get is something like this. So here's sliding speed again on the x-axis, and this is shear strength. What it does is originally the strength increases, the resistance increases, until it reaches this dotted line, which is the Coulomb strength of the till, and then it continues on from that point. This is the experiment with no class, right? So where we don't have those big rocks. When we put the rocks on there, we get the same general response, where the resistance quickly rises, meets the failure strength of the till, and then rides along the failure strength of the till from that point forward. It gets there sooner, meaning at a lower sliding speed, than when there was no class. So the class at the ice bed interface are having the same general response as no class. It's just causing the bed to yield at a slower sliding speed than when there is class presence. So this is both of them. And so when you look at this model, what's going on, which one of these is it? It's both, right? You have this rate strengthening component of the ice moving around those class and moving around those bumps at the ice bed interface until the traction that the ice exerts on the bed is sufficient to cause the bed to yield at this point, this transition velocity, at which point you have a steady resistance beyond that point, a bounded resistance. The weakest link in the chain is initially the ability for the ice to slide around the class and then becomes the till itself yielding. When we have big class, you get something like this. When we have small class, you have the same general response, but the transition velocity is slightly higher. Again, because the ice can't concentrate the stress on the class as efficiently when they're small, basically. So you can think of it on the left side of this, we have the ice kind of sliding over the till that's not yielding because the ice hasn't exerted enough stress on it to cause it to fail. Whereas on the right side, it's a combination of the till yielding, and the ice is still going to slide over the top of it, right? Both things are going to happen. So how can we represent this behavior? It's just a minimization, right? It's a minimization that says that the strength is the minimum of whichever one of these two things is occurring. Is it the rate strengthening component right here, where it scales with the velocity, or is it the frictional strength of the till, the Coulomb strength of the till? Whichever spot you're at dominates. What we really need to know is this transition velocity, because that predicts where one mechanism takes over for the other. The nice thing is that we can solve that, right? We know the mechanics of how these class plow through the bed. There's stress imparted on the ice by the ice, or imparted on the class by the ice flowing around. There's some known strength of the till. And this problem is similar to what civil engineers do when they run a cone penetrometer test. And so the mechanics are basically identical to what civil engineers do all the time to figure out the bearing capacity of like buildings and stuff like that. This is the relationship for the transition speed. There's a bunch of stuff in here. But the important part is that there's no tunable variables in this. It's explicitly predictable. If you give me a sample of till, I can tell you what the transition velocity is, right? We know things about the viscosity of the ice and the bed. If we know the grain size capacity, we basically make one measurement, which is this NF, which is the bearing capacity of the till. It's a standard measurement made in civil engineering. And we can tell you what the transition velocity is. And you don't have to tune it, right? If you had a piece of till, you could figure out what this transition velocity should be. It depends on the class size. As the class gets bigger, you can the transition velocity changes a little bit. So this is basically a representation of what happens if you have several different class plowing, right? You can have big class plowing, this black line here, small class plowing, this black line here. And if you have a range of class plowing and you average them together, you get something like this red line, which gets rid of this curve, this inflection point, which is not realistic in nature. So this turns out, this is hard to put into a model, this minimization, and it's hard to use it to make a prediction off of. And so some response that looks like this, called regularized Coulomb, where it has the components of the till strength in it here, but also has this velocity strengthening component here, but depends explicitly on whatever that transition velocity is, allows you to make a prediction that looks like this, that's a continuous function, right? Doesn't have that inflection point, it doesn't have that minimization in it. So this is what, if you use that model and you make the prediction from all the things you can measure, you get these lines. These aren't best fit lines, these are predictions from that theory that are compared against what we were measuring in the experiments, right? So this is the model with the class, this is the model without the class, and these are the data points. And so there's a pretty good fit between the ability for the model to make some prediction of what the sliding speed looks like and what's recoverable in the experiments. Okay, so the next thing is that model, that idea of the ice sliding around class and included in the bed, is predicated on this idea that the base of the glacier, the ice has no debris in it, right? And every time we look at the base of a glacier, that is not the case. The base of the glacier always has debris in the basal ice, some component of it. And how does debris in the basal ice change this problem? So this is Ingebreen Glacier. This is a spot in ice in Norway where the Norwegian government drilled a tunnel underneath a glacier, and you can go under the glacier and melt out a big hole and be underneath a glacier and measure things. This is the basal ice. This is the ice above it, and this is the bedrock. This is what basal ice looks like. It doesn't look like that perfectly clean material I showed you in the last one where we idealized it in the lab. It's got all sorts of dirt and debris in it that are changing things like its rheology, its mechanical components. And so if that idea I just put forth of the ice sliding around a class and the ice is viscous, if you push this around the same class, how is that going to change those mechanics? Is it going to completely invalidate them? It could, right? It's perfectly reasonable. Here's an idea. And so here's the ice. Here's this frozen fringe. Your very own Colin Meyer's favorite subject. And this is the unfrozen deforming material below it, right? And so people have found this sort of ubiquitously, right? Here's Thwaites Glacier in Antarctica. This is the sub that they drive around. It's kind of washed out, but this material has all sorts of basal material in it. Here's Pope Glacier, a core that was pulled out. Here's some things looking through Willans. Basically, everywhere we've looked in Antarctica and everywhere else, there's at least some debris in the basal ice. And, so this seems to be ubiquitous. This is what the bed of a glacier looks like, right? So this is a three-dimensional scan using a white light profilometer looking down on a slip surface after one of these experiments. It has all of this complex roughness in it, right? And the roughness is because the till has some range of grain sizes. That roughness changes how the ice couples to the bed, but it also affects the mechanics of how material is able to be entrained in it. So Colin, along with his postdoc advisor and collaborator Alan Rempel, have developed these theories for how the ice can be entrained in the basal ice and what that process is. And so imagine you have the ice up here and you have some zone of sediment near the bottom of the glacier. That roughness that you see here, just like I showed in the last picture where you're looking from above, gives rise to some radius of curvature. That radius of curvature changes the surface energy of this area and affects how the ice can infiltrate into this sediment and incorporate it into the basal ice. This idea stems from this concept of pre-melt films that exist here. So the melting point of a material in a small particle pore, like you have here, is lower than the bulk melting point of the material due to the increase in surface energy that these particles give rise to. And so very fine pores have high curvature, like this, and that results in the liquid phase being thermodynamically stable in these conditions at a temperature that's below the bulk freezing point. That invokes a temperature gradient in here, and it evokes the ability to draw water towards this interface. And it also has this interesting feature where as you move down in the frozen fringe, the amount of ice that's saturating the pore space isn't constant. You have higher saturation of ice at the top of the frozen fringe, and it decays with depth. This curvature also gives rise to something called a critical entry pressure. And that's what you can think of is the ice, if the ice is pressing on the bed with a certain effective stress, it can infiltrate. And then it presses a little more, it can't infiltrate. And then it pushes a little more, and it surpasses this critical infiltration pressure. That's when the ice can start to grow this frozen fringe and develops in this pore space over time. That gives rise to sort of a temperature gradient in the frozen fringe, like I was saying, that affects the ice saturation within the pore volume. So this ice saturation goes like this. So this is a temperature gradient that occurs, and you basically can change the ice saturation in this porous volume by this frozen fringe giving rise. Why is this important? It's important for what we're going to talk about today because this ice is effectively clogging the pore volume up. And if liquid water is trying to move through this system and the pore volume is clogged by water, it can't move through it very efficiently, right? It has a harder time moving through it. So what does that do? How does that affect this sort of slip response that we might expect to see, right? Once we add this frozen fringe to the bottom of the ice, sliding over the deformable ice, we've sort of shown it's ubiquitous. I didn't talk about it here, but we've shown that all Collins theories are effectively right, that that's essentially how you get it into the bottom of the ice. But what does that do to actually changing the frictional response? You can imagine, we talked about before, we have this regularized Coulomb response. Now we've added this very debris-rich ice sliding over this interface. Does it behave just like a Coulomb material? Does the ice no longer effectively matter in this situation because you're effectively sliding very debris-rich ice that probably should behave like a Coulomb material over a granular material that we know behaves like a Coulomb material? And so when I go back to this question, now we add this frozen fringe to the bottom and see how this complicates the overall picture. So we want to determine a slip law with ice with a frozen fringe this time, moving over the bed. So we again use this ring shear device. But in this instance, we grow a frozen fringe at the basal layer before we slide and then see how that affects this drag response like we've seen before. So again, we've done experiments where we use glass beads. We've done experiments where we put till in it. We do the same thing. We grow a frozen fringe for 4 to 6 weeks. We impose a range of driving stresses. We impose a range of effective stresses and look at the resistive drag the bed can provide when we have a frozen fringe in this instance. So here's the ice moving from left to right. This is the frozen fringe that was grown. There's a small zone of deformation that's below it. And below it is the till that's unsaturated or water saturated, not saturated with ice. This is what it looks like after we pull it out. So this is the frozen fringe we've grown. It's got these really interesting sort of structures, microstructures that you would find in it. And this is what it looks like sort of in Dougal's hand, basically. Here's a video of the frozen fringe with the glass beads. So the ice is moving from left to right. We have this glass bead situation. We have this deforming zone below the frozen fringe, and then we have the till below it that's unsaturated. Okay, so here's the response, right? So here's again sliding speed, and this is the frictional resistance, and that's the Coulomb strength of the till in this case. And it's not a Coulomb material. Like if you had asked me beforehand, I don't know what would have happened if you asked Colin, but if you asked me, I would have thought everything would have just plotted on this line. But that's not what we see. We see, again, this rate strengthening component, And then we see it reaching sort of this Coulomb threshold stress beyond that, just like we did before. So it's, even though the basic idea we put forth with this plowing doesn't hold up in this case with the debris-free ice, it still has the same form, right? Not only that, when we're in this Coulomb regime, we do experiments where we systematically increase the effective stress and look at the frictional response, and for both experiments with and without class, and we get this linear response. And so it tells us pretty conclusively that when we're in here, it is really behaving as a Coulomb material, but not when we're in this area when we're moving slower. So what's going on? What's causing this rate? This caused us to wait. I mean, not wait. It took us time to figure this out. By we, I mean, it took Colin some time to figure it out. So you had to tell me what happened here. But it goes back to this idea of what's happening in the frozen fringe and how this ice saturation is affecting the mechanics of the frozen fringe. Because effectively what it means is this frozen fringe is somehow weaker than the underlying till for some portion of this regime. Now, in this spot, this is depth, so this would be in the frozen fringe like this. This is the ice saturation. So the ice saturation is high at the top and it decays as you move down. And that's, again, clogging up the flow space. And that's hard to move the water through. And so what that does is it causes the water pressure to increase in the frozen fringe beyond what it would be in just the natural till, because the pore volume that the water wants to move through is all clogged up with ice, basically. And so you have high effective stresses at the top, low effective stresses at the top that decay to the normalized value at the bottom. And so this makes the fringe mechanically weaker than the underlying till. We put it into this response here for basically what's derived for permafrost deformation, where we have some strain rate. It's a function of the saturation of the ice, which we can get from sort of Colin's model of how this works through the system. We can rearrange it and solve for some integration that allows us to estimate how the velocity in the frozen fringe would vary through strain that's accumulating in the material as it's deforming. And that makes a prediction that looks like this. So we recover this rate strengthening component from the frozen fringe by essentially clogging up the pore space that's occurring in it. Now you can use this and you can actually figure out what the speed of the frozen fringe is at its base. And if you use that as this transition speed in this other form of the slip law we got before, you get this dashed black line. And so this gray line is from the model without the frozen fringe that I showed you before. And it doesn't fit the data well, right? Here's the data points for these triangles. This is the prediction from this Zoet and Iverson 2020. But when we put the mechanics in it for the frozen fringe, we get this really good agreement between the data, the triangles, and the dashed line that's model prediction. So it helped sort of unify why we still get this regularized Coulomb response, even when we have this heavily laden debris-rich ice sliding over the bed. Same general flip law can be applied. It's just a different mechanism that's controlling this transition velocity. Okay, the last part of this is trying to understand what happens to slip when you're close to the ocean, right? So in the area near the ocean goes up and down with tides, which basically floats parts of the ice shelf, and that affects how stress is distributed in the area that's up zone of the grounding line, in the grounding zone, and even a little farther up ice. People have sort of made attempts to look at this with these idealized models of viscoelastic flexure, where you move the tide up and down, and that transitions the ice being pressed into the bed in some places and lifted off the bed in other places. And so what does that mean? It means, like, say you have the till at the bottom and the glacier sliding over it. There's some spots where it's being compressed as the tide is lifting it up, and then as the tide goes down, it uncompresses it. So instead of the effective stress being constant, it is oscillating on the bed in response to how the tides are varying the front of the glacier. And so in this experiment, or in this situation, you can imagine what we want to do is not only simulate sliding at a given speed or rotation at a given speed, but then simulate what happens when we pump the system. We diurnally pump the system like is happening in nature. So we do the same type of experiments, but the effective stress is no longer held constant. It's actually oscillated, using that ram at the bottom to see how the bed is responding to it being oscillated. So we want to determine the slip law for ice moving over deformable beds with varying effective stress, or varying effective pressure. So not constant. It's sort of oscillating with time. And again, what we do is we use this machine, but we use this ram at the bottom. It's hooked to a fairly sophisticated pumping system, which we can program and tell it to vary the pressure however we want. So we keep it on, for these experiments, we'll keep it on a 24-hour period, and then we'll change the amplitude of it. So first we'll pump it at some amplitude, and then higher amplitude, and then higher amplitude. All the while the glacier, the ice is spinning, and we're measuring the frictional resistance to it. And then for all these, it's at the same speed, right? We're not changing the speed. So here's time on the x-axis, and this is the effective pressure that's in the system. So you can see initially we have these relatively small amplitude oscillations. Then we have bigger amplitude oscillations. Then we go up. Then the pump runs out of fluid. So this one gets screwed up. We do it again. So we do 2 extra ones here to sort of compensate for this thing crapping out in the middle of it. And then we measure the drag that results from this. Okay, so when we look at this drag, here's a different type of plot. This is effective stress on the x-axis. This is how hard we're pushing on the system. And on the y-axis is the resistance the till is providing. Now, if the system was in steady state at all times, what you would expect to see is as we're pumping the system, the value would just travel up and down this straight line. It wouldn't deviate from it, right? If it deviates from it, it means that there's hysteresis in the system, right? Something more complex is happening from pumping this system than you get when it's just steadily sitting there like it is probably farther up ice where you don't have tidal effects. We get a loop that looks like this. It's not in steady state, right? The glacier is not it's in these hysteresis loops in the area where you're oscillating the stress. This is when the stress is increasing, and then we start to decrease it, and it looks like this. And so it does this variability, right? And again, these are realistic values for how the stress varies. It's the right sliding speed. It's till. It's got the right hydraulic permeability. It's just literally till we dug out of the ground that has all the characteristics that till has. And in this range of all these things being basically right where they're supposed to be, you're getting this hysteresis loop. Here's one of these loops. Here's the 3 of them stacked on top of each other. They sort of follow the general cycle. Sometimes we're calling it quasi-steady state because a loop follows itself over and over and over. And again, remember, this is as it's moving, as it's sliding over the top of each other. What do we think's happening? We think what's happening is in the granular material, that material is being deformed, right? And as you compress it, what happens? All of the water in the pore space has to get out, right? If you start to consolidate the till, you're making that pore volume smaller and smaller and smaller. And the water has to flow away or get out or get to the surface interface or something else because it's being consolidated. But the water can only move out of the system as fast as the hydraulic permeability lets it. And so if the hydraulic permeability is low and you can't flux the water out fast enough, you build up pore water pressure. You build it up not artificially, you build it up beyond the steady state. If your pore water pressure goes up, it means your effective stress goes down. So the effective stress is the ice pressure minus the pore water pressure. And if your effective stress goes down, your strength decreases. That's why when you're compressing the system, you're actually making it weaker, right? Because you're trying to get the water out, and the water can't get out fast enough. So it carries the load, and the load gets taken away from the granular material. When you unload the system, because the system is shearing, those grains are trying to dilate back to a critical state porosity. And the opposite's happening. As it's dilating, it's trying to suck the water back in, and it can't suck it in fast enough. And so as it dilates, as it mechanically dilates, the pore water pressure goes down in the pore space. And that causes the effective stress to go up, and that strengthens the till. So when you're lifting off the till, because you're dilating it, you're actually making it stronger because you can't get the water into it fast enough. And so people have looked at this, civil engineers have looked at this. A common way to do it is use Terzagh's consolidation equation. This is sort of the fundamental equation in soil mechanics. which basically relates as you load a system. This is the applied stress as a function of time. You can look at this sigma UE, which is the excess or reduction in pore pressure. So how much that pore water pressure builds up or lowers from the steady state relationship as you compress the system or as you dilate it. Now, the thing that's nice about that is if you can figure out how this pore water pressure is deviating from a steady state, you can make a prediction about what the drag should do, how that resistance should go. So simply by solving this equation and varying this in time, just like you have with that oscillating stress that you're applying on the system, you can recover how the pore water pressure is changing and affecting the overall strength. However, you need to know two things. You need to know the compressibility of the system, of the skeleton. As you press on it, how much does it respond and consolidate? And you need to know the hydraulic permeability of it. Again, all these things are measurable. You don't have to estimate them at all. You can use devices like this. So these are called consolidometers or odometers to do consolidation tests. And you just systematically increase the load on the sample, and you watch how much it consolidates, and you watch how long it takes to consolidate. It consolidates based on sort of the mechanical properties of the system, and how long it takes to reach a steady state is dependent on the permeability. And so you can estimate what this coefficient of consolidation is by putting it in this very simple soil mechanics apparatus. If we do that, so we've measured this for the till we used in the experiments, and then we put it into that solution, and we drive it, we get hysteresis loops that look like this. So this is the effective stress of the system. This is what the response is, right? And this is a model, but there's nothing, everything in here is measured, right? There's no wiggle room to get this to be different. And as we increase, this is being driven by something that's very similar to what we see in the experiments. We get hysteresis loops out of the system that look very similar to what we see in the experiment. But by very similar, I mean almost exactly a match, right? And so this loop right here is being driven by the experiment that produced this loop right here. And they have the same amplitudes. They have basically the same range in effective stress. They have essentially the same distance across here. And so this very simple model can recover almost all of these complex mechanics that we see in the experiment by just measuring one simple thing in this odometer, essentially. You don't need to do these oscillating tests anymore with a complex ring shear. You just need a basic odometer in, an undergrad civil engineering student for a week, right, to figure this out, essentially. Oh, my week's this is my department's lecture. Yeah. Okay. So, overall implications. The sliding has a component of rate strengthening before the cooling behavior dominates, right? There's a transition velocity, this u sub t, between the two types of slip, and it can be estimated from these plying mechanics. No need to make a generalization. Frozen fringe still results in that regularized Coulomb behavior, but the Coulomb strength is reached at a lower velocity than it is when you don't have debris in the ice. It's pushing it closer to Coulomb, actually. Generalized rule can be used to approximate the proper physics in a way that ice sheet models can be used because this regularized Coulomb is a pretty easy way in a continuous function to be implemented. In the grounding zone, there's a cyclicity. The cyclicity of that effective stress can lead to actually greater strengthening and weakening than you would experience in steady state. So all these mechanics are sort of changing in the grounding zone because of this pumping that's going on. And so what overall we found is something like this regularized Coulomb does a good job when you're talking about steady state, and something like a Coulomb response is probably pretty good too if the effective stress is particularly low or the water pressure is particularly high. And you can iterate on this if you're in areas where it's transient, like at the grounding zone of glaciers. So with that, I'll say thanks. This is part of my group. This is Dougal. He's the one that did some of these experiments. That's Colin. He helped with the other ones. And then Natasha's not on this picture. So thanks. I'll take any questions. Yeah.